27 years ago, physicists made one of the most shattering discoveries in the history of cosmology. They were measuring the distances to faraway galaxies using Type 1a supernovae, exploding stars so consistent in their brightness that astronomers call them standard candles. Think of a standard candle as a cosmic light bulb. If you know how bright it really is, the dimmer it looks, the further it must be. The idea was simple. Measure how bright these supernovae appear, compare it to how bright they should be, and you can figure out their distance. Do this for hundreds of supernovae across billions of light years, and you can map the expansion history of the universe. Everyone expected to find that the universe's expansion was slowing down. Gravity should be pulling everything back together, right? But instead, they found the opposite. Distant supernovae were dimmer than expected, meaning they were further away than they should be. The universe wasn't just expanding, it was accelerating in its expansion. Something was pushing the universe apart with increasing force. They called it dark energy, and this discovery won the 2011 Nobel Prize in Physics. For almost 3 decades, cosmologists built theories on that assumption. But there was a problem with those supernovae. A problem nobody noticed until just now. Dark energy became the biggest mystery in cosmology overnight. It makes up roughly 70% of the total energy density of the universe, but we have no idea what it even is. The leading theory suggests it's a cosmological constant representing the energy of empty space itself. This energy doesn't dilute as the universe expands. It stays constant. So as space grows, there's more dark energy pushing outward, causing the acceleration to increase forever. This became the lambda CDM model, the backbone of modern cosmology. But there were always cracks. Different measurements gave slightly different expansion rates, a problem called the Hubble tension. And now, corrections to decades-old data suggest that dark energy might not be constant at all. A team of astronomers in South Korea re-examined those same Type 1a supernovae, the same standard candles that revealed the accelerating universe in 1998. And they found a problem. Type 1a supernovae aren't as standard as we thought. They're affected by the age of the stars they exploded from. Younger stars produce dimmer supernovae. Older stars produce brighter ones. Since looking at distant galaxies is also looking back in time, this age bias meant we were systematically misreading the data for decades. The team analysed hundreds of supernova host galaxies and confirmed this age bias at over 99% confidence. Then they applied a correction, and when they did, the data completely changed. The corrected supernova measurements no longer fit the lambda CDM model with a cosmological constant. Instead, the measurements aligned with a model where dark energy appears to weaken over time. And here's the paradigm shift. When they combined this corrected data with other independent measurements from the cosmic microwave background and baryon acoustic oscillations, the new model shows that the universe isn't accelerating anymore. It's already slowing down. If confirmed, this is a paradigm shift on par with the original 1998 discovery. It means dark energy isn't constant. It evolves. It weakens with time. And the universe's fate could be completely different than we thought. Instead of expanding forever into a cold, dark oblivion, the universe could eventually stop expanding altogether. Gravity might start winning again. Some models even suggest the universe could eventually collapse back in on itself in a big crunch. But we may be getting ahead of ourselves here. This is just one study. It needs to be confirmed. Fortunately, more data is on its way. The Vera Rubin Observatory in Chile just started operations with the world's most powerful digital camera. Over the next 5 years, it'll find tens of thousands of new supernovae, letting astronomers test this theory precisely. If this age correction holds, it doesn't just change our view of dark energy. It resolves the Hubble tension, explains long-standing inconsistencies, and opens a whole new chapter in our understanding of the universe. So it's not just, is dark energy weakening? It's, if the expansion of the universe is already slowing down, what comes next? What do you think? Could 3 decades of cosmology have been built on systematic bias? Let me know in the comments, and subscribe for more deep dives into discoveries that are rewriting our understanding of the universe.